Cool, so welcome to, where are we? What is this universe? Did you have a good break? Yay. Good. Cool, so you might be aware the following weeks until the completion of the module will be today with me, then 3 weeks off. I'll be in China, and Bruce is seemingly taking 2 of those lectures, and Mac Acoustics are bound to come in to deliver a lecture as well. Mac Acoustics is the acoustic consultancy company of Bristol with fairly significant success and clientele. So they will give you some insight into the industry side of things. And then on the 19th of December will be the last class, and I will be back for that. And then the module is completed, at least the teaching of it is. And then you'll be pretty much on your own for the assessment, for the portfolio of measurements, 2 out of 4, I've introduced that already. So that's another month. And if you feel a bit shaky about this assessment, probably best to start already. And then when I'm back on 19th of December, I can, help you out significantly, or, make sure that everything is fine. Okay, because actually from that 19th of December until the 15th of January, I won't be available. And that's pretty much the submission. I'm not even sure when the submission is. So in any case, if you think you will need some assistance, or at least also if you think that you will want to do a very good job, then I do advise that you do the basics in the forthcoming month, and then we can chat about how to make something exceptional as well. Okay? So that's the plan. We're nearing the end. To me, it seems like it's the end already, for obvious reasons. Cool. So as far as the topics go, the last 2 lectures with me, including this one, will be about gear. Okay, so we are taking the stuff that we've learned about spaces, and we are going to perform similar tests with gear, hardware or software, starting today. So, would anyone potentially remind us, what is it in gear? What is the main phenomenon that happens with electronic transmission of signals that does not happen with acoustic transmission of signals?
Non-linearities.
Yes, non-linearities, excellent, right? So the space does not distort. In fact, if you really want to be accurate about these things, suggested, then use the term, as I never do, non-linear distortion. That would be the term that is more precise. Hello. I used to do this. Whoever comes late has to tell us a joke. You guys feel inspired? Oh, there's a really bad one coming.
Oh, I definitely do have a joke.
That was funny. Okay, so non-linearity or non-linear distortion is the crucial term that describes what? What happens when a signal gets non-linearly distorted? Harmonics arise. New spectral components arise. Okay, we also have intermodulation components. So that's the thing, you see. So what happens in space is linear and typically time invariant because the buildings don't move much. Which means that actually what's happening in buildings, in acoustics, in acoustic transmission, is filtering. Right? Can you think of an acoustic amplifier? Can I think of an acoustic amplifier? Can you think of a mechanical amplifier? Yeah? Well, that's the tricky one, right? That's a really tricky one because it's a passive thing. So can you call a passive system an amplifier? Because it does not inject energy at all. It transforms energy. And it can transform energy in a way that it appears louder to us. That's certain. But technically, it is not really an amplifier, even though the body of the guitar does, practically amplify the sound of the string. It's a passive system. So it transforms the energy in a way, right? It transforms kinetic energy. That's what you give it, right? You give it motion, kinetic energy. And it transforms it into acoustic energy. Now, the point is that a single string is a very inefficient transformer at that, and you don't hear it very well. Now, if this kinetic energy is transferred through a bridge onto a very thin timber plate, that type of transmission does give us audible sound, does give us the impression that the sound has been amplified. So actually, I'd buy it, especially if I have a half a pint before that. Sure, guitar amplifies it, whatever. Right? It's not really that crucial whether it's yes or not. I think what is crucial is your ability to see different perspectives and to articulate different perspectives. Right? So we're not in the game of yes or no, win or lose, the best object, the worst thing, and all the rest. We are in the game of reflection, hopefully. Okay, that is as a matter of introduction to what is going to be. And actually, it's going to be fairly simple. Today, we're going to deal with filtering characteristics that arise from electronic equipment. And then in the last session, we will look at the actual nonlinearities, at the distortion components and such. And maybe at that stage, probably you will potentially use software as the object of analysis. So today, it's going to be hardware only. Cool. So let's start briefly with the conclusions from the last session. Who remembers anything at all from 2 weeks ago? Nope. Zero. Yeah. Cool. Well, we're in the same boat, luckily. So I'll just read through and hopefully things will come to mind. Okay, so we were looking at suitability of whole for lecturing first, which kind of reads speech transmission, kind of reads speech intelligibility already. And then what we've done is we've taken different listening positions. Okay, and then I kind of left it open and I said produce a combined graph, right? Previously, I always told you how to and what kind of graph, but now we're coming to the end and I'm trying to make things a bit more challenging. So I didn't really tell you how to combine those graphs. Does anyone remember? I think all the groups had to be talked to. That's a horrible term in English. I think that means assassination, right? You need to be talked to. Before it transpired, what is the way of combining these graphs? So what was the point? The point was that the first idea that came to most minds was, well, average it. Starting to ring bells? Why was averaging the bad idea? Exactly, right? So what we were looking at clarity. Okay, as a matter of reminder, clarity is an acoustical quantity and it describes clarity in the way that the energy is split at a time threshold. And for music, for speech, that is 50 milliseconds. For music, it's 80. So C50 is your speech clarity, so to speak. And what happens is that you essentially take the impulse response, you look at the energy in the first 50 milliseconds, and you look at the energy after the 50 milliseconds threshold. Okay? And the clarity is the ratio of the two. So the more energy in the first 50 milliseconds, the more clarity. That's how it is defined, and that's how it works. Okay? So what we had in REW is a spectral clarity display. So we actually had a measure of clarity per spectral band. So we actually had a graph of clarity rather than a single number. Very often, if you go through some acoustics related materials, you will find a single number describing the clarity. And in fact, also it's a bit tricky because sometimes you see it as a ratio, sometimes as dB. It's not even very uniform, I would think. But in any case, the more clarity, the more early energy, the more late energy, the less clarity. Okay? So we were looking for anomalies. We picked random spots in the room with variation as much as possible. And we were actually looking for where it goes wrong. We were looking for the anomaly. Is there a frequency band for the given spot where the clarity is very low, right? So if I have multiple graphs describing this and I average them, what happens is that those anomalies are lost in the averaging process. So when you look for anomalies, don't average. What was the good way? What would have been the good thing to do with these graphs? To obtain and essentially highlight the anomalies. It would have been the minimum graph. Okay? So you had 3 graphs that describe a single spot. And we are looking for anomalies in terms of insufficient clarity. So the best thing would have been to take the, kind of connect the lowest lines, so to speak, the minimum graph of the 3. Because then the worst case points will come through, because that's what we're looking at for. Okay? Now, in REW, taking the minimum graph is not an available button. So you could export to Excel, export back, blah, 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 do these things. You don't really have to. But the easy solution was, anyone remembers what was the easy solution? Pick the most anomalous one. Okay? Now, with a bit of a caveat there, because it happens, as you know by now from experience, that for some inexplicable reasons, one of the graphs does not make sense. So there is this thing where it's so anomalous that it's suspicious, right? So that's why we're also developing this kind of intuition that okay, it can be bad, but it can't be that bad. That's a measurement anomaly rather than the anomaly that you're looking for, okay? But in this case, it was a good choice to pick the most anomalous graph. Okay, and then we could produce appropriate combined graph for each listening position. And then something that we didn't quite get to, if I remember right, would have been the variance of spectral characteristics for the spots. Okay? So here again, the challenge is to read through the question or the instruction with attention, because I'm actually saying spectral characteristic, I'm not saying clarity, right? So here probably the first thing to do, we'll just do something with those clarity graphs. But actually here I was looking for the variance of the spectral characteristic. What is variance of spectral characteristic? So it would be for each of the frequency bands, it would be the distance between the highest and the lowest value. So if you kind of observe the graphs as a sausage, then it would be the thickness of that very sausage. So the variance is the difference, the maximum difference. Okay? Why would we ever look for variance of the spectral characteristic in this context? Well, typically most of the spaces have the problem of different spots being largely different. Okay, so it's typically the biggest challenge, and I've just seen one of the Rick Beato's things. I kind of like watching this guy. with the guy who was mixing Tina Turner, I don't know, on big stadiums, whatever. And he said, well, there is one thing, mono. And he said, well, if one guitar player, is panned left and his fan base is on the right, I'm spoiling their experience. They won't hear the guitar. So actually, this guy said that big stadiums, I'm sorry, mix mono. That's what they do. That's what this guy does. Why? Because of this. Because of the variance across the audience. Right? So that's typically what you're trying to identify. Is it very bad or not? The variance itself. Okay, and then there was one really exciting thing. I think maybe one group missed on it, but the other one got it. I don't quite remember. What happens very close to a wall in terms of clarity?
More clarity. More clarity.
More clarity, exactly. Why? Because the reflection that you get from the side wall is early. But what's bad about being very near a wall? I should probably ask this in plural. Well, one thing that we've seen is comp filtering. Okay. Why is comp filtering lesser at a distance from a wall than near a wall? I mean, obviously the comp filter frequencies would be different because the path difference is different, typically larger, so lower notches. But why is it lesser? Because of the level differences of the reflected sound and the direct sound, right? So to get a full comp filter, you can't get a full comp filter when it actually nulls, goes to -infinity dB at a given frequency. This is possible only if the reflected and the direct sound are of the exact same level. So the further you are from the wall, the lower energy there is in the reflected sound, therefore lesser interference, therefore lesser of a comp effect. Okay? So that's one thing. What's the other thing that's problematic near a wall?
Boundary effect.
Namely?
Low frequency.
Low frequencies, yes. I'm not sure if the boundary effect is the right term there, but I might be challenged. It might be. I haven't. It kind of associates towards something different for me. But in any case, the proposition is right. You will get much more bass. Why? Well, actually, there is two components to the answer. The straightforward thing is because the reflected energy is in phase for bass frequencies, right? Because, I don't know, 20 hertz, what is the period length of 20 hertz? Who knows? It's quite a bit. What was it? Was it 34 hertz is 10 meters? Something like that? That sounds right. I'm in a funny mood today, do excuse me. So many meters, right? Which means that within a single meter or half a meter, it is largely in phase, right? So the bass frequencies are in phase, therefore constructive interference with the reflected sound, therefore more bass. Okay, and this is probably more than sufficient to remember, but for those of you, and I probably can point a few who really want to know much more, it actually also has to do with the fact that the ear is a pressure device. Because if it was a velocity device, it wouldn't sound louder next to the wall because the velocity wave is at its minimum against the wall, where the pressure wave is at its maximum against the wall. How could we ever imagine an ear which is a velocity detector rather than pressure detector? Hint, think of microphones. Which type of microphone is a pressure microphone? Dynamic, well, it depends on other things as well. It typically relates to the directivity And omnidirectional microphones are typically pressure microphones, which means that the back of the capsule or the back of the membrane is sealed. Okay, so if the back of the membrane is fully sealed, what that means is that the pressure arriving is being measured. So how is it different? How is the pressure gradient microphone different? Pressure gradient, the gradient of pressure is velocity. Beautiful terms. It is different in that the back is open. So actually you're not detecting pressure, you're detecting the difference between pressure at the front and at the back. Okay, so that's your pressure gradient microphone. So if our membrane, our eardrum was open back end, it would probably be more of a velocity device. By the way, it is just a bit open through Eustachian tube, which is actually your DC filter. It makes sure that your ears don't burst when you fly. They just hurt a bit instead. Okay? Cool. Variance, single graph, clarity, 4 listening spaces. Looking good? Excellent. I'm really happy. I think we're tackling some really exciting topics here. Any questions, comments, ideas? A big no. All right. Cool. So yeah, let's get on to what I have planned for today. And if there are not much questions or points of discussion, thanks to the funny mood, we might start the practical session earlier. So what we're going to do is we're going to try and assess the filtering characteristic of a mixer channel strip or an EQ. So I've talked to Isaac next door, and there is 3 mixers and there is 1 EQ. So every group can choose what they prefer if they're first to choose. And what we're going to try to produce are graphs that look a bit like what we had when we did the obstacle. All right? So just as a reminder, let's briefly look at that, what happened there. So we're going to work kind of backwards. So instead of me telling you exactly how to get to that graph, I'm going to draw what you want to get to and see if it works. I mean, obviously you can look back at that practical and kind of look at the steps. And it's about dividing spectrum. So as a matter of reminder, what we had there is at low frequencies for different distances from the obstacle, the response was pretty much the same. And then if we inverted the graph as needed, arranged it well, it transpired that there were things like this happening for different distances. So we kind of got a graph looking a bit like that. Okay? So that signified the fact that as we get nearer the obstacle, so this is the nearest. So I'll do, let's say, 5 centimeters curve, 15 centimeters, whatever, 25, 35 centimeters. So each curve represented a given distance from the obstacle. And if you got sufficiently far away from the obstacle, it didn't really act as an obstacle. Okay? So this is the type of graph we are looking at making today, but with a filtering. So actually, I don't even have to draw a new one. If I have a low-pass filter going, or a kind of a high-frequency dial on the mixing panel, then this should read as 0 setting, depends on the grading on the hardware. Maybe this is -5, -10, -15, and -20. Okay? So we're going to try to obtain a similar curve to this. I'm asking you to pick 2 bands, so you can take the mid band, the low band, the high band, whichever one you like, and do the measurements accordingly. Okay, so it's actually slightly shorter setup time, I believe. I didn't really spell it out. I kind of expect that at this level you guys can do this anytime. So obviously you take the sound card, you take the output of the sound card into your EQ, and you take the output of the EQ to the input of the sound card, right? So we're replacing the microphone speaker system with a single device essentially, and running the REW thing. Okay, you can do that. It doesn't have to be in space with microphones and all the rest. Okay, and then look at these graphs, and essentially, you know, verify that what you expect is happening is actually happening. Okay, so one thing you can do then is actually get this scale, figure out what is the attenuation of this given device. And the second thing that we will look at will be the cutoff point. So here is a little, how should I say, a slightly provocative intent on my part, because the big books read that the cutoff point of a filter is at 3 dB. Why is that? Any idea? Why would be filter cutoff point where it already cut off by 3 dB? The reason is that all filters start to act very gently. The best things in life are gentle, right? So what happens is that you can't really pinpoint where it starts because it starts so gently. What you can pinpoint is the minus 3 dB point. Okay? So who can predict the joke that is going to unfold from this thing? So what I'm asking you to do is take different settings in terms of amount of filtering. Oh, by the way, this will probably look like this as well. Right, so you have a boost as well on the mixer, but you'll figure that out. What's the joke here? Well, the joke is, and we'll see, you know, how your graphs look like exactly, but if I filter minus 5 dB, I might get a minus 3 dB point here at 1.1 K, and if I filter minus 20 dB, the minus 3 dB point might be at 1K, which is obviously stupid because it's the same old filter and the cutoff point is not different just because I've changed the amount of attenuation. That's my little provocative intent here. Okay, but I'm interested to see, you know, how different groups will find this, and you know whether you can pinpoint that minus 3 dB and how bad it will be. You know, I mean, obviously you could go further and say, well, if I don't filter, well, actually, kind of makes sense. There is no cutoff point, right? But if I filter really gently, if I filter at minus 2 dB level reduction, then where is my cutoff point? Nowhere to be found. Well, probably against some or other limit of transmission. That's actually quite interesting. At one point I was looking, because the air also has a cutoff, but I think it's, I don't even know, I probably shouldn't say unverified stuff at this stage. Okay, so that's that. So random EQ setting, 3 measurements. So the first thing, all right, that I skipped, so I've explained the 1.2, that's pick 2 bands, measurements at 5 different equally spaced settings, which is typically 1, 0, and then 2 above, 2 below, 1 extreme, 1 halfway. That's how I envisage it. And then showing the level increase and decrease, so that's that graph. I've explained the cutoff point, which is a bit of a joke, but nevertheless potentially a funny one. I didn't explain 1.1, which is this baseline thing. Okay, so the thing that I want you to briefly look at is something that was quite surprising in space, namely that you ran the same measurement twice, 1 minute later, without anything changing about the setup, and you got some variance, right? You looked at the difference of the 2 graphs, or actually not even the difference, just the 2 graphs, and you saw that in a very low base, it's just a mess, and often at very high frequencies as well, it was a mess, okay? So that was this attempt to figure out the baseline, right? Because if I figure that without changing anything, two measurements give me up to 10 dB variance at 20 hertz, then I know that my measurement at 20 hertz is reliable to that degree, namely not very much at all. Okay? So it's kind of establishing the baseline, also just making sure it's a kind of a sanity check, right? So try that sanity check on the hardware. I'm really curious to see if there will be unexpected things, because the expected thing is that these are quite reliable in that sense, and you should be getting a fairly flat 0 dB difference between two measurements without anything changing. Okay? And then you place a quartz crystal next to the device and post a myth-busting video about most of those things. Okay, so that's the sanity check. So try that too, and then see the difference in a single graph, make a claim on precision. You can say, well, this is fairly accurate throughout the spectrum. Cool. So 2, 3, 1. I told you I'm in a funny mood today. And then 1.4 will be about DC coupling. Okay, you might have encountered this term before. In hardware, DC coupling means that a fixed voltage at the input will cause a fixed voltage at the output. Okay? So DC direct current has to do with fixed voltages. AC has to do with alternating current, which is essentially vibrations and sound. Okay? So DC typically is not sound. Okay? However, there are some myths around DC coupling as well. Typically, if you're into modular synthesis, you want your things to be DC coupled, because you combine audio signals with control signals. And control signals can be very slowly evolving or fixed. And if you have non-DC coupled modular gear, you can't do that. Okay? Now, so what it does, if the device is not DC coupled, it means that fixed voltages will be not transduced. I shouldn't say transduced. They will just disappear. At the output, you won't measure a fixed voltage ever. Why is that advantageous? When is that cool? That you don't have fixed voltages at the output. Well, it's really cool for the speakers, and I actually believe the ATCs are DC coupled, so this term does apply to speakers as well. How do you test the speaker for being DC coupled? Well, you just give it a fixed voltage, and if the membrane is displaced and stays there, then it is DC coupled. If the membrane is displaced and crawls back slowly into equilibrium position, then it is not DC coupled, and that's your actual DC filter. Okay? So for most speakers, it is safe not to have a DC coupled output, because you just sent it a fixed voltage and it struggles. It's kind of displaced permanently. On top of that, if there is a DC component, which is the term that we use when we express the fact that the zero line is not the zero line anymore, so the average of the signal is displaced, it means it has a DC component, then you're more likely to get distortion, because you're actually not using the range of motion of the membrane symmetrically, but you're actually pushing it against one or the other extreme. Which is really cool because it gives you second harmonics, even harmonics. We can talk about that. I'll probably talk about that in the last class. Okay, so that's your DC coupling thing. So I'm asking you to test your little mixer channel strip or EQ for DC coupling and to figure it out yourself. Okay? So we'll see. Obviously, if you get there, I'll be attending to the groups and I can help you with that. So I'm giving an increasing amount of open tasks, as you have noticed, which by now is custom with task 2, where you have to design the whole experiment. And in this, I'm asking you to design an experiment to assess the issues arising from aged faders and dials on hardware equipment. But we can discuss it briefly. Any ideas about this one?
It'd have to be a comparison, wouldn't
Is it? With?
it? Like newer dials and not.
Well, it could be. I mean, you could also expect a new dial not to produce any anomalies, but actually it's a good call because they probably would. But if you were the engineer in a studio and the client comes in and he says, I'm suspicious about this 30-year-old desk having issues with faders, could you please quantify that?
You do it so you put a signal through it, say halfway, and then full, like I say, on a channel fader, halfway up and then all the way up, and then cancel the SPL difference and like see if it's got a difference in frequency response.
Okay, so cancellation with inverted phase is probably what you're hinting at, yeah? So that's something that is a good testing procedure in general. But let's try to be focused and systemic about this. So what are the types of anomalies? Let's start with that, and then we can talk about how to detect and quantify each one. So the first thing are linear anomalies, which is essentially filtering. Okay? So that is fairly straightforward. That's what you're going to do with the EQ setting 0. You just look at whether the transfer is flat or not, right? You don't really expect a fader to filter lows or highs or anything like this. Who knows? It may happen. If the guy has the cash for you to try it, why not? Okay? So filtering. The other thing is distortion anomalies. Now, whether you expect a distortion from a fader or not, nonlinear distortion arising of the harmonics and intermodulation components, actually, yes. Actually, every electronic resistor will give you some nonlinearity. It might be unnoticeable, it might be even difficult to measure, but theoretically, yes. In fact, they induce noise. Okay, but that's the next chapter. So briefly, just to wrap it up, you could measure the distortion. Maybe it distorts. Okay? And then we come to what we call intermittent distortions. Okay? One of them is noise floor. Okay, so every resistance in electronics will produce some noise. So you can measure that, potentially. Back to the old question, how do you measure the measurement equipment? My favorite question. So, noise floor measurement, obviously you would have a really high spec measurement device. The sound cards that we use aren't high spec measurement devices, as you might know. However, we do have a Prism Sound 3D scope living with us, and it is a bit abandoned. It used to live in my office for a while. And in fact, I got a PC just to be able to use it because it doesn't run Mac, unfortunately. But that is a serious sound card that measures sound cards. Practically, that is the measurement device. And they're very famous for one of the most best ever clocks as well. And sound devices, sound cards are the only ones that I'm aware of that are actually calibrated. Shall I tell you? I think I have the time. I should tell you about this little experiment I've done, because I'm a bit disillusioned by the graphs that supposedly tell you stuff. Okay? And I probably expressed this a few times already. Now, on the other hand, the gap between psychoacoustic fidelity and the technical fidelity is another thing I've been mentioning that I'm very much aware of. So I was thinking about coming up with ways to sonically assess anomalies which are inaudible, right? Because the thing is that if I have a Prism sound card and an RME next to each other, I didn't really try the proper blind test, honestly. I should have. I need an assistant. Anyone? So the thing is that I can't tell the difference. But there probably is a difference. It's just inaudible. But I don't want to look at a graph that shows it. I want to hear it. So I was thinking about ways to make the inaudible audible, because I'm not interested in the graphs. I want to hear it. So what I've done is I've coded a bit of Super Collider that played back 2 seconds of a sound and recorded it back again. So I had the sound card looped with a cable, output to the input, and then do it again, and do it again, and do it again. So I was re-recording the sound card with itself. And long and behold, after 50 iterations, Prism sound did beat RME audibly, right? And actually, it's the kind of anomaly. Oh, and by the way, I had a digi-design thingy, in the drawer. So for the sake of, that's the one that you can hear immediately to be ulterior. It beat it by far, 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 far after 50 iterations. So that was this thing when I discovered something that I didn't anticipate, that for the other sound cards, I actually had to code an adaptive gain because it went either to infinity loud or to silent. Because, no matter the fact that everything is at 0, let's say, output, input, whatever, I could not make a setting where it would reliably stay on the same gain. Because you imagine if I 50 times re-record with the same gain settings, and if there is a 0.1 dB more or less in the process, it will just escape to infinity, either way. So all the others, they had to use the adaptive gain, whereas the Prism sound, lo and behold, did not. It absolutely stayed at level to infinity. No issues with that. So it was properly calibrated as well. So, there is engineers and there is engineers and there is marketing and all the rest. The bad news is that they claim the sound card back. So part of this experiment went to, could you please send me one of your sound cards for testing, which they did. But the bad news is they claimed it back. I was hoping it would kind of, stay with me. But that didn't happen. And in the end, I didn't buy a Prism sound because I typically don't do 50 iterations of re-recording for my mixing and production. But
RME have got slightly more stable drivers than us.
Drivers are supposedly the forte of RME, yes. And I can attest to using 15-year-old RME sound cards with 15-year-old computers on FireWire 400 still to this day, and it being far more stable than anything more expensive than 200 quid altogether, because that's the price of it now. If you buy 15-year-old FireWire 400 recording iMac and RME sound card, if you're lucky or addicted to eBay like myself, then you get that for 200 quid, right? And to buy that new, it's 2,000 quid, right? So it's worth considering. The bad news, the good news is that it can't run YouTube either, which means you won't be wasting that much of your studio time with random shit anyway. And in fact, it's a challenge to run a browser these days. So on a 15-year-old architecture, I think I'm running 10.8 somewhere, and you need to find a hacked Firefox version to get online at all, right? But actually, my recommendation is don't have your studio computer online anyway. It's the only thing it can do is mess it up. And by the way, this 15-year-old computer running 10.8 starts up in about 3 seconds from the moment of pressing the power to it starting up. It's beautiful. Okay, how about that? Any questions, any ideas? Is there anything interesting to discuss about this hardware stuff? Oh yeah, we didn't really finish this one. obviously. It's a funny day. So we talked about filtering. The fader doesn't typically filter. Who cares? Try it. The fader typically does not give you extra harmonics. It does not do nonlinear distortion. It typically does give you a bit of a noise floor, right? Which is actually a funny thing. I thought I liked the idea, but in the end I don't. You will find that some active close field monitors do not have a gain control in the back, and they're always full on. And initially it seems like a bad idea, because if you accidentally run a full volume telephone into that, it will burst your eardrums, right? So you really have to be careful. The reason why they do that is not to save the cost of a fader. It is this holy grail of minimum noise floor possible. And they actually do it to avoid the noise floor that a single fader will induce. Now, it's a kind of, what's the term there? It's some kind of prophecy, I don't know. In any case, the issue is that you actually in the end get more noise floor, because the sound cards don't give you noiseless signals. So you have to drive your sound card really soft not to burst your eardrums, which means that you're actually amplifying a whole lot of noise. So I'm kind of having my doubts with this design these days. In any case, noise, yes, faders do cause noise, but actually it is more about what we call intermittent distortion, right? So it is about crackling, right? That's the worst thing about faders. I mean, you're looking at me as if you've never trashed a DJ mixer in your life, and if you haven't, I advise you to do that very quickly, promptly. Get on eBay and trash a DJ mixer like that. It crackles, you know, it goes, there is anomalies. So how do we quantify that? How would you attempt to quantify that? If the client asks, well, he says, if you say, well, actually, I don't hear it crackling, and the client says, well, I'm not so sure about that. Let's measure it. How do you measure that?
Sigma change for it and turn it up and down and record the result.
Well, that's the thing. One thing you can do is you can say, well, actually, I can measure the level of crackling against the noise floor of the gear if I don't send any signal through it, right? But the funny thing is that faders will crackle more with the signal coming through them, typically. I'm not sure if I can fully understand why at this stage, but I might tomorrow. The point is that a silent test may not be sufficient. And if I play Tina Turner through it, how do I measure the crackling of the fader?
Do you like have your test audio just flat, and then you have your test audio running through whatever piece of kit that you're testing, and then compare the difference?
Well, I think you've hit the gold thread. Is that an expression? A mine? Whatever. I think you're thinking in the good direction. You said test signal. What is a test signal? And this was the first lecture, if you remember, analytical signals. Analytical? I think it's analytic. We are analytical, signals are, I don't know. In any case, what test signal?
Simon.
Why?
Because you can analyze it by the spectrum analyzer and see any anomalies rather than...
Well, wait a minute. So how do you expect... We didn't quite talk about a fader doing pitch shifting, but it's a largely unexpected one as well. So you wouldn't expect it to change the pitch of the sine wave, I assume.
The waveform, wouldn't it?
Well, if it changes the waveform, that's nonlinear distortion, and you detect that by looking at harmonics. Now, what you could say is that what I want to have a look at is the linearity of the fader. So you can say, well, I'm going to look at the gain of the sine wave going up as I'm pushing the fader, but a bit difficult to quantify, is it? So sine wave, why? What was the other things we have? Noise. Noise? Why? Impulse? Impulse. Why? The thing about sine wave, which is really cute, is that you can discard it at the output very easily. So I can push a lot of energy into the system, a very loud sine wave, and at the end, I just notch it or don't look at that frequency. And I look at all the rest. So actually, I'm displaying what happens in the system when a lot of energy is being input into it, except at that one frequency. So that would be probably my call. In fact, this kind of notch filter-based analyses are done on harmonic distortion. I mean, in previous decades, we didn't quite have the digital equipment on par with analog. So a lot of these techniques, testing and measuring techniques, have their analog counterparts. And notch filtering the input sine wave is one of the standard things, right? So you can actually have a really loud sine wave at the input, completely notch it out at the output, and you get to see what it has done to the system otherwise. Okay? And then what? Take a hammer and smash the fader. Like, oh, you thought it made a, you thought it was anomalous. Well, now it is, right? Because obviously you would have to jerk it quite a bit to get to the maximum impact that the crackling of the fader may have, which will make the issue worse. So how do you measure the measurement equipment in a different configuration? Okay? So yeah, just, you know, I mean, obviously I'm trying to contextualize these things in some professional practice. And, you know, we're trying to be very engineering and measury and analytic. So hopefully this kind of expands your perspectives on that as well. Cool. Any questions, suggestions? Wicked. So the gear is with the text. Go and grab it, and I'll give you a hand in a minute.